Alright, so today we're going to talk about the volume of rectangular prisms. We've been talking a lot about the surface area of different three-dimensional solids, but today we're going to shift gears and start talking about a different type of measurement, and that's volume. But before we do that, we're actually going to go all the way back here to perimeter and area, and we start to think about, when I said perimeter, I wanted you to think about a fence. That's the distance around the outside of a two-dimensional figure. Okay, so if we wanted to, it's a linear measurement. If we wanted to start just counting or measuring with a tape measure or a yardstick or a ruler, we could just count up the 5 centimeters that make up this side, and then keep counting right here, these 3, then we'd have a total of 8, and then count this 5 more, and then we'd have 13, and then count back 3 more, and we'd have a total of 16 for our distance around the outside of a shape. That's why we think about a fence, right? And there's different formulas we can do there, 2 times L plus 2 times W, or just perimeter equals length plus width plus length plus width, right? But anyway we get there, it's just basically counting up the total distance around the outside of a shape, which is different from floor tile, or from area, which when I said area, I wanted you to think about floor tiles, because we're no longer measuring a straight line, okay, that linear measurement. Now we're actually measuring squares. So if we had that same shape that was 5 by 3, that same rectangle, now it's like imagining that each side, okay, this 5 and this 3, if we actually measure out the centimeters and draw these lines in here, we're now actually counting up how many 1 centimeter by 1 centimeter squares it would take to cover this entire figure. So now we're measuring in those squares. Another way of thinking about this is we just counted up 15 squares that are 1 centimeter by 1 centimeter in size. Each one of these squares is 1 centimeter by 1 centimeter, and there are 15 of them. That's what 15 square centimeters means. Again, that's the number of 1 by 1 squares that would cover that same figure. All right, so we've been dealing with perimeter and then area, and then we moved on to surface area. And so when we were talking about perimeter, I said think about a fence, and we were talking about area, I said think about floor tiles. Now when we said surface area, I wanted you to think about wrapping paper, because we're still dealing with square units. Still square units when we're doing surface area. We're just now finding the area of each of the surfaces that make up each of the faces that make up that three-dimensional shape. In this case, it's a prism. Okay, and we also found surface area of pyramids as well. But this is a rectangular prism, and we found surface area of triangular prisms and other shapes as well, because it's basically just as simple as breaking it down into the different faces that make up the shape, calculating the area of each one of them, and then adding them all back together. And so we took some shortcuts along the way. And I drew this one a little different because we're going to use it with our volume example, but it's the same concept here. We found the front and rear. Okay, so we knew this front rectangle, which has that same length of 5 and width of 3, or base of 5 and height of 3. So that had 15 square units on it, right? We just saw that on our last sheet. Okay, now we're also imagining that there's one of those in the back, and that's again how this drawing is a little different than some of the ones we've been using, but we know there's another rectangle on the back side of this box that needs to be wrapped in paper too, and it also is 15 square inches. Oh, that one says inches. Should say centimeters, right? Okay, and so that's the front and rear, and then we're also imagining the right and left sides. Okay, so on this right and left sides here, I have a measurement of 3 by 3. So a base of 3 and a height of 3. 3 times 3 is 9, but that's just the right side here. Remember, I'm imagining there's also one of those on the back here, a 3 by 3 rectangle on the left side. And so I'll multiply by 2, and I have 18. That would give me both the left and right. And we did the same thing for the top and bottom. So here's my top of 5 by 3. So here that is 5 by 3 is 15 square centimeters again. And I have 2 of those. Again, I have one on the top, one on the bottom, so it makes a total of 30. And again, surface area, all I was doing is adding the area of each of the 6 surfaces of this rectangular prism together, and I end up with a total in this one of 78 square centimeters. And that's still telling me, just like when we were doing area here, okay, floor tiles, that's still telling me how many 1 centimeter by 1 centimeter squares it would take to cover now the surface of each face on this prism, or again if it was a pyramid. And so now today is when we really shift gears though, because now we're going to move into a different unit of measure again. Volume is measured in cubic units. So when we thought perimeter here, I wanted you to think of a fence. When we hear area, I said think of floor tiles. When you hear surface area, you think wrapping paper. And now when you think of volume, you're going to think sugar cubes. Okay, sugar cubes are actually really nice to think about because they're right about 1 centimeter by 1 centimeter by 1 centimeter cube. And that's what we're dealing in now is cubic units. How many 1 centimeter by 1 centimeter by 1 centimeter cubes would it take to occupy the same amount of space as the prism? Before I get into that formula, I'll just show you some examples of this here. So my good cubes are all at school. I built some here out of paper. And if we like just stack all these cubes together, oh, I'm missing one. There it is. Okay, we can make a rectangular prism. This particular rectangular prism, okay, has a length of 2, a width of 4, and then a height of 1. And there are 8 then total cubes, right? And we could even calculate the surface area of this if we wanted to as well. Could rearrange these cubes into another rectangular prism. This one's actually a cube, right? It still has a volume of 8 of these 1 by 1 by 1 cubes. And so if we were going to measure something like this three-dimensional solid and say what is the volume of this, what we'd really be measuring is we'd be saying about how many of these cubes would it take to occupy the same amount of space as this volume. Now I didn't make that many of these cubes. It took me quite a while just to build all these. You can just kind of see, imagine this here. If we were trying to find the volume of this rectangular prism, like, all right, well, how many of these 1 by 1 by 1 cubes would we have to stack together to take up about that same amount of space? Right, and keep stacking them in here. Okay, and so if you kept building more of these, you're like, okay, how many would it take to occupy that same amount of space? And basically what you're saying is, yeah, Mr. Green, you're just seeing how many of it would take to fill it. Well, kind of. I mean, if that's what you want to equate it to right now, you can. But that's actually, when you were talking about filling something up, that's actually capacity. And capacity and volume are just a little bit different. And some of you would maybe understand that right now. Capacity would be measured, I can't squeeze these ones in here, but you see, you get the idea here. Capacity would be like when we start measuring things in like milliliters, those types of measurement, which aren't cubic units, right? Cubic units, we're seeing like how much space it takes up, how much space this object would take up, now not how much it can hold. Capacity is how much it can hold. But for right now, like if that's helping you like see this, you're like, okay, well, we're trying to see the volume of this shape. We want to basically see how many of these cubes it can hold. That works. I mean, if that's going to help you kind of understand this at this point, that's an okay analogy to use, okay? So, what does this look like when we start putting it back on paper? So we're measuring that volume in sugar cubes. We're seeing if we have a rectangular prism like this one, how many 1 by 1 by 1 cubes would it take to fill that, or to occupy that same amount of space? And in this case, I used the same measurements that we just found the surface area over here. And I used the formula for volume, which is volume equals the area of the base times the height. And I've talked about using specific capital letters or lowercase letters at different times because they usually signify something if you use a capital letter. Like when we used A over here and it's a capital A, that means area. Or when I was calculating perimeter, the capital P means perimeter. And we know that. And then the small b and the small h means base times height, right? Or the small L or the small W means length times width. When it's a capital B here, that actually stands for area of the base. And this V stands for volume. People that are looking at your work would know that. Okay, that's our language we're talking in here. But the bonus here, and so that'll work for any prism. Okay, the volume equals the area of the base times the height, whether the base is a triangle or an octagon or a hexagon or a pentagon, and then times the height, as long as we're defining the height of the prism as that distance between the two parallel and congruent bases, which gets real easy when we start dealing with rectangular prisms. This is going to be one of the easiest things we've done in quite some time, because the formula now, if I think about it over here, the area of the base times the height, the formula now becomes, what's the area of our base? Length times width. We're dealing with a rectangle, right? So it's length times width times height, which is just multiplying three numbers, which I'm pretty sure we can all do all right here. Volume equals length times width times height. So I come back to my drawing. Here's the length times the width times the height. So 5 times 3 times 3. 5 times 3 is 15. 15 times 3 is 45. Oh, but check out that label I put on here. 45 cubic centimeters now. So we've shifted from before when we were dealing with square centimeters. Now we have cubic centimeters. And we actually talked about this a little bit when we were working with exponents earlier this year, that instead of reading something to the third power, you can read it as cubed. Just like instead of reading something to the second power, we often read that as squared. When we have a 3 as our exponent, that means cubed. And this is why, because we're talking about a third dimension here, a length times a width times a height. So this is a 1 by a 1 by a 1 cube that helps make it up. And actually the reason I drew this particular picture is you can see this formula in action really easily right now. You can imagine this. It says length times width times height, all right? Well, my length times my width, I can actually I could count these if we do this top row. I have 1 cube here, 1 cube here. I can see two sides of them, right? 3 cubes, 4 cubes. Here's a 5th cube that I can see 3 sides to. 6 cubes. Here's a 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th. There's 15 cubes, right? That's the length times the width. There's 15 of those cubes. That's just in that top layer. So what the height is then asking me is, how many layers are there? Well, here's one layer of 15, plus another layer of 15, plus another layer of 15. That's why I'm timesing it by the 3 again for the height. So I have my area of the base, which in this case is 5 by 3 is 15. Then I multiply the height because there are 3 of those layers, which gets me to my 45 cubic centimeters. And so to start, we're really just going to focus on volume of those rectangular prisms. And so your assignment today, I'm going to give you a couple of chances to even pause and copy down some of the stuff that I have on here. But your assignment today is going to really ask you to break down a few of those rectangular prisms that are drawn with the cubes first. So it says in exercises 1 through 3, rectangular prisms are made using 1-inch cubes. So we're assuming that this is 1 inch by 1 inch by 1 inch. So each one of these cubes that you can kind of imagine even in the back here, those are all 1 inch by 1 inch by 1 inch cubes. It says find the length, width, and height of each prism. Well, the length even tells me L. Nice, that's 5. I can count them. 1, 2, 3, 4, 5. The width and the height of each prism. So here's the width right out in front. 1, 2, 3. And then the height. Well, it's 1 tall. Okay, and this says find the amount of material needed to make a box for each prism. So if I were going to wrap this, if this were my gift, I don't know what kind of gift that would be here, but if this prism were my gift and I was going to wrap it for somebody, and again I wanted to cover it all with no gaps and no overlaps, that's what surface area is. I'll go right back to what I just reviewed on here for surface area: front, back, left, right, top, bottom, right? So we have the front and back. Well, that's just 3 by 1. Okay, but there are 2 of them, one in the front, one in the back, so I multiply by 2. The left and right, here's a 5 by 1. So 5 square inches, but there's 2 of them, a front or a left and a right. And then the top and bottom, so I have 3 by 5 for the top, and that's 15 square inches. And then there's 2 of them, one on the top, one on the bottom. So I would need 46 square inches once I add those all together. 46 square inches of wrapping paper to cover this prism if I were giving it a gift. But now the new thing for today, that's all reviewed, and the new thing for today was the volume. And I wrote it in right away before I even used the formula on this one because I could count them all. You could see all these boxes right here. You could see this, or these cubes. see this 1 by 1 by 1 cube right here, and you can count up 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I knew there were 15 1 by 1 by 1 cubes, or 1 inch by 1 inch by 1 inch cubes to take up that space. That's what volume's measuring, right? But here as a review, and you can pause it here and copy some of this down if you need to. Volume equals the area of the base times the height of the prism. Well, the area of the base is a rectangle, so that's a length times width, which is 15, times 1 high in this case. There's only one layer of those. So it's 15 cubic inches, 15 1 inch by 1 inch by 1 inch cubes that it would take to fill up that same amount of space. Now, when you start looking at these, don't freak out. We can count 1, 2, 3 by 1, 2, 3, 4, 5. So we can find the length of 5 again. I'll even give you some of these here. The width of 3. And this time the height, they're stacked 2 high, right? And so for the surface area, I would just repeat front and back, left and right, top and bottom. And I have to say, okay, there's a 5 by 2 side, a 3 by 2 side, and then the 3 by 5 top and bottom. And make sure, you know, for each one, for the left and right, the front and back, top and bottom, that you multiply by 2. Count for all 6 sides of that prism, and finding that square, the area, surface area in square inches. But now for volume, again, it's 5 by 3, which is 15. I can even count these 15 cubes on the top layer if I want to. And then how many layers are there? There's 1, 2. So without even doing the formula, again, I know this has a volume of 30 cubic inches, which I think I skipped that part of the direction here, but that is the third part here, which is find the number of cubes in each prism, the volume, and that's just reminding me what it is when we're finding the volume. It's how many cubes are here. Now that was the first page of this assignment. I'll let you work through the surface area on number 2 and both the surface area and volume here on number 3. And then I'm going to, again, leave this out here for you for a second. If you want to copy down some of this work, you can pause and copy down some of this work for 4 and 5. Don't show you the cubes, but they ask you basically the same 2 questions. They didn't ask you the length and the width and the height, because they gave them to you in the drawing this time. But the surface area, we've been working on this for a couple weeks now. We're going to find the area of the top and bottom, the area of the left and right, the area of the front and back, and then we'll add them all together, and that's my total surface area. Some of you on your assignments, you're actually doing a really nice job of organizing your work to find the area of the front and back, left and right, top and bottom, but then you weren't giving me that total surface area. You weren't adding them all together. Make sure we're doing that. And then for the volume, this is where it's the new concept today is kind of the easiest thing we've done in a while. It's the volume equals area of the base times the height, but it's a rectangular base, so you don't even need to write that really. Just for a rectangular prism, we need to remember the formula is volume equals length times width times height. So I have the length of 4, the width of 2, that's the dimensions of my base, and then here times 4 for the height of my prism, because the height of our prism is defined as that perpendicular distance between the 2 parallel and congruent bases. So in this case, that's 4. So now I have 4 times 2 is 4 times this 2, which is 8, and then times this 4 again, which is 32. So 32 cubic inches will be the volume for this one in number 4. Okay, so then you'd have one more to do on your own. So you got, again, number 1 we did together here. Number 2, I gave you some hints on, but you need to find that surface area. Number 3, you're going to be doing all on your own. But again, it still has the 5 by 3 base, so it's still working off the same model. It's just stacking them a little bit higher. Number 4, we gave you there. Hopefully you can copy down that work. Keep it nice and neat and organized. And then number 5, you'll have to do on your own as well. Same kind of idea, though. Okay? Good luck with volume of rectangular prisms.